So good afternoon. Thank you to all of you on site and online. I'm delighted to welcome Professor Olga Fink. Olga is a tenure track assistant professor and the head of the Intelligent Maintenance Operations Systems Lab here at EPFL. Her talk today is entitled Domain Adaptation and Hybrid Algorithms Fusing Physics-Based and Deep Learning Algorithms for Diagnostics and Prognostics. You know the format. We have roughly 45 to 50 minutes seminar, and then we have time for questions. Our speaker kindly agreed to take urgent questions directly during the talk. So if you're on site, just raise your hand, we'll try to figure in. And if you're online, just raise your virtual hand and we'll try to get you in. For that presentation, I would like to thank Olga, of course, for her availability, and once again, the CIS team for making all the logistics happen that allows us to have this event. Now, Olga, the floor is all yours.
Thank you very much, Jan, for the kind invitation and for the opportunity to share some of our research with you today. Also, thank you very much for everyone for the interest and for attending in person and hopefully discussing afterwards a bit more. So that's the research questions that we're actually dealing with, and the title is a bit long, but I will walk you through what it actually means, and it has in fact two parts. But what we normally are really interested in is, on the one hand, to detect faults, so to detect if there is something wrong or if there is an anomaly in the system. It could be such a simple system as the railway wheel. But then also to diagnose, and diagnosing is distinguishing between the different fault types. In this case, if it is a flat, if it is non-roundness, if it's shelling. And this already helps the maintenance team much more. But then also finally to predict how the system evolution, system condition is going to evolve over time. And this is really the last step and the most challenging one as well. And the systems that we are dealing with, as you already saw, is partly railway systems. We're also looking in hydropower plants. We're looking in power systems. So whenever something gets complex, and also if there's sufficient data that is collected on the system, and data is on one hand condition monitoring data, but then also operational or usage data that is collected on those systems. And recently, particularly deep learning has become quite an enabler to solve some of the challenges that we are facing. And if you look into deep learning models, what they are typically very good in is in distinguishing between patterns with labels that we already know. But in our case, since what we're really interested in is faults, and faults then are our labels. And since we also look into safety critical systems quite often, since they are usually quite complex, and this is where we're also interested to prevent the faults from happening. This is where faults are usually missing, or they are very rarely occurring. So it's really not possible to collect a sufficiently representative data set of all these different faulty conditions so that we can start learning from them. And then what is more, if we are taking in a new system into operation, this is where we typically will not have any fault examples from that specific system. So what should we do there? Because normally, if we have a quite advanced condition monitoring system, then this is what we are selling to our customer. And then we would be telling him, maybe you need to wait for 1 year or maybe for 2 years until we have collected sufficient data to start training our algorithms. And what is more is that often, even if we have collected data that is representative at the point of time when we train the algorithm, all these complex systems typically have quite a high diversity of operating conditions. So they're, and often they are operated with regimes that they may not be even designed for. So then we start collecting data that is really quite dissimilar to what we trained our models on. So this results in some of the challenges that we're trying to address. And on the one hand, it's missing labels, but it's not just missing labels, but it's really missing samples with fault labels. So it's not just we have sufficient images, and we're just missing someone who labels them, but we just don't have those classes and fault conditions. We're also facing the challenge of this high diversity of system and operating conditions. And what is more, since these are engineered systems, typically those who are using these decisions are supposed to take decisions after the algorithms have provided some output. They also require some interpretability of what they're actually getting. And since we have this quite high diversity of operating conditions, we are really facing the challenge to make our models as generalizable as possible. And often we're even required to extrapolate beyond the regimes that we trained our algorithms on. And there are several solutions to these challenges. And what I wanted to discuss with you today, actually, two of these solutions and two of the directions that we have been working on. And on the one hand, it's domain adaptation. And on the other hand, it's those hybrid approaches where we're combining physics-based with deep learning models. And I will start with domain adaptation and go down. I'll elaborate the second part. So let's imagine we have a new unit, and we would like to apply a machine learning fault detection or fault diagnostic algorithm on that. We don't have any data, but we may have had some units that would have already operated and have collected some units. If we have a new wind turbine, for example, we probably have already had some wind turbines in which we collected data before. So in that one, we may have the labels, we have a trained model, and then we take this trained model and then we apply it to the new incoming data of this new unit, this new wind turbine, for example. And what is often happening is that they're typically operated under different conditions, under different regimes. They're not possibly the same wind farm. So what is often happening is that the performance drops quite significantly. And this is not something new. This has already been observed in computer vision, where, for example, if you train an algorithm on these clean images and then would like to apply it to these images collected in the wild, the performance drops. So what we would like really to achieve is to align these two domains and then to overcome this domain shift that we're actually facing if the unit is not operated in the very same way. So this is where domain adaptation approaches have been developed for and quite extensively in computer vision applications. And for us, domain would be different operating conditions or different units. And one potential direction is also if we have a trained simulated data, would like to apply them to real collected data. So these are our domains, and what we would like to achieve is that we would like to overcome this domain gap and this distribution shift. And what we are always assuming is that on the source domain, on the target domain, we don't have any labels. We only have labels on the source domain. So this is really the setup that we are dealing with. So in the first case, let's take a look into how does it apply in the most basic setup. And in this case, we are assuming that we have full data on our source unit or source operating conditions and would like to transfer them to the target unit to new operating conditions. And one of the best performing algorithms in domain adaptation, and also the one that's been probably applied to a lot of different applications, have been the domain adversarial neural network. And what they do is they combine two parts of the loss functions. On the one hand, we have this classification loss. So this is the task that we are really interested in. Then we have the second part, and this is our domain classifier. So while we are training the algorithm, what we would like to achieve is that the features become indistinguishable between the source and the target domain. And how it achieves that, so it applies a very elegant but also rather simple trick. So it applies the gradient reversal layer. So what it does, it basically flips the gradient. So this is why while we are minimizing the misclassification loss, We are also we are maximizing the domain classification loss, and this was what makes the features between the source and the target indistinguishable or aligned between each other. So let's take a look, how can we apply it to our setup? So we have a source data set, and on the source data set, we have labels and we have healthy data, and we also have labels for the different fold types. And what we also assume is that we have a target unit or target operating condition. But what we also now assume is that when we're developing the model, we already have observed all the different fold types, so that the data on all the different fold types has been collected, but we don't have any labels for that on the target data set. We only have labels on the source data set. So we applied this approach to a bearing benchmark data set. It was a data set collected in a test rig from the case Western Reserve University. So it has 10 different classes, 1 healthy class and 9 fold classes with 3 different fold types. And for each of the fold types, there is 3 different severity levels. And there are 4 different loads, and we are assuming that each of the loads would be 1 domain. So what we tested it on is the transfer between the different domains in all the different directions for these 4 load domains. And what we took as a baseline, this is the case when we train the source, when we train the model on the source data set and don't do anything else. And what you see is that already the performance of the baseline is quite high, so it's 95%, which also means that the domain gap between the 2 domains is rather small, so it already performs quite well. However, if we now apply domain adaptation to it, we're able to improve the performance by around 4%, which is quite a significant performance bar. This performed rather well, but this is rather a non-realistic setup under real conditions, since typically if we are taking a new unit into operation, what we may have available is just healthy data and not all this full data on the target unit that we haven't observed yet. And this is what actually is also referred to as partial domain adaptation. So this is the first part here. So we were considering here that on the source data set, we have all the different fold types with labels. On the target data set, we have all the different fold types, but without labels. And later we are testing on the target data set, again, on all the different fold types. But in the real condition, what we are rather facing is that on the source and the experience unit, we have all the different fold types observed and also the labels. But when we are developing the model, we may really just have the healthy data that we observe. But later on, once we develop the model, we would still like to apply it to all the different fold types and not just to the healthy conditions that we actually observed when we develop the model. So this is also referred to partial domain adaptation, since the label set on the target data set is not fully covered. And in the extreme case, what we're actually having is that really we just have the health condition. And it has been addressed a bit, the partial domain adaptation in other applications as well. However, this extreme case scenario that we only have 1 class available during the model development time, this one has not been addressed. But again, later on, when we're testing it, we would like to apply it to all the different fold types. Again, we have this algorithm that actually works quite well. So the domain adversarial neural networks, and we could actually apply the same algorithm to our setup as well. So this is the original case, and everything that you have, see that here in gray, those are the fold types that we haven't observed yet, but that we expect to be present in the target data set as well. So if we then perform our domain adaptation, what actually happens is that it gets misaligned, because during the model development time, we don't have the full information. So it really gets misaligned. And what we proposed in this case is to preserve the representation of the source unit, because this is where we have all the fold types that we already have observed. And then we can fix it, we can preserve it, and then instead of bilaterally aligning the source and the target, we just unilaterally aligning the target to the source. How do we do it? So we train first the feature extractor on the source data set, then we fix the features, and then we impose a consistency loss between the features that have been learned on the source feature extractor, and then between those that are now learned in the domain dataset we're training, and we still keep the other two parts of the loss, so the classification loss and the domain classification loss. So we just get a third part of loss, which is our consistency loss, in order to preserve the representation that we learned from the source domain. So we can then again apply it to the very same setup, and now we have still the same data set, but now we're assuming that when we're developing the model, we only have the healthy condition available, but we are testing it on the entire classes, or on all the classes, so on all their 9 fold classes plus the healthy condition. And the baseline remains the same because this is still what we had available. We trained it on the source domain and then applied it to the target. But now if we apply the unilateral alignment, this results now in a performance improvement of about 3%. So it's a bit below what we saw before, but now we have much less information that we actually use for. So this setup seems to work and work rather well. But what we may also face is that possibly we need to exchange the fold patterns between different units of a fleet potentially as well. So now we are assuming that we have an experienced unit. We would like to transfer the experience to the inexperienced ones. But what may happen in real applications is that some units may be experiencing some of the folds, some other units may be experiencing some other folds, and now we would like rather to exchange between them. And this is where we started considering a bit different ideas. It's not quite domain adaptation, but it's applied to domain adaptation. And the general idea is that actually our faulty signal could potentially be represented by two parts. And one part would be the domain-specific variations of the normal condition, and the second part would be this the faulty signal that could be potentially be domain independent, so that we could have the fault signal that could be extracted and could be transferred between different units or different operating conditions. And since we typically are dealing with high frequency data, particularly for the acceleration data, for example, if we consider this in the Fourier domain, what we put as a hypothesis is that a fault signal could be represented by two parts. On the one hand, the domain-specific healthy signal, and the second part would be the domain-independent faulty signal. And we also put a scaling factor to adjust it to the conditions. So then if we start generating new fault conditions, what we actually would just need to generate are these faulty signals because these healthy signals we typically do have available when we are measuring or collecting the data. So this results in the proposed architecture. We refer it to as the fault signature gun. So it applies the gun learning step, and what we're actually learning here is particularly this fault signature, and we are generating samples for the different classes of the different severity classes. Then we are adding additionally this healthy conditions, and then we get the combined fault signal. And then we can apply the discriminator here, so to distinguish if it was a true or generated signal. And we still have this classification loss here, and this is the fault classification here. So it looks actually quite nice, but as you remember, what we are really starting with is that on the target data set, we don't have any true classes or any true fault samples. So then we would not be able to train the discriminator because we don't have any real fault samples to discriminate between. But what we also assumed was that actually this fault signature is independent of the domain. So what we could actually do is we could train this GAN architecture on the source data set. Because this is where we have labels available. And once we trained it, because we are assuming that this fault signature is independent of the domain, we could then start applying it. So then we still apply to generate these fault signatures, but now we can add any of the healthy data to it, and then we are getting the real fault sample. So that's the basic idea. So on the one hand, we are assuming that we have the domain dependent and domain independent part, and that the domain independent part is the fault part, and we train it on the source data set, and then we can apply it to any of the target domains. And since we do it this way, we can actually apply it really in all the different setups, so not just in this partial domain setup that we just looked into for the domain adaptation part, but we can also start transferring it in the different conditions because we learned we can learn it between the different domains, and we can really transfer it the fault conditions domain independently. So we can also apply it to this open and partial, where we have only partly overlapping feature label set, and then we can transfer from the one, or we can generate fault samples in the one or in the other domain as well, and then test it on all the different fault types. So we applied it again to a bearing data set, but this time we applied it on a bearing data set that has a larger domain gap compared to the CWIU data set, really to be able to demonstrate how it actually performs under this setup. So here we have 4 different domains. We have now a bit less classes, so it's just 6 classes. We have 2 different fault types. One fault type has 2 severity levels, and one fault type has 3 severity levels. And in fact, this domain 1 is actually the one that is the most similar to it. So a lot of the other studies that have been working on the data set have rather excluded it from their consideration. So we actually performed 2 parts of the experiments with it without that domain. So this is the resulting task that we are trying to solve. So we are still in the setup that on the target domain, we only have the healthy target conditions. So we first tested on the partial domain adaptation task. So we have on the source data set, we have all the different labels for the fault types. And now we're generating synthetically these different fault types here. And later on, we are testing it on real data over all the classes. So let's take a look on the performance. So the baseline is now really much lower. So it's at 80% compared to the CWIU data set. If we apply the unilateral alignment, so that's the approach that presented to you in the second step, the performance improves already, but not so much. The fault signature gun improves again, but again, not so much. It's a bit better than the unilateral alignment. If we now include this more dissimilar domain, and we now only look into all the transfers for this domain 1, where the operating conditions are more different to the other. So the source conditions, the baseline now drops quite significantly to 40%. Now the unilateral alignment is able to improve the performance by 10%, which is quite a big jump already. But then the proposed approach is actually able to improve it by more than 20%. And now we also wanted to take a look into how does it apply on this open partial domain adaptation setup. That we have partly overlapping labels between the source and the target. So what we assume is that on the source unit, we only have the inner ring faults, and on the target unit, we only have the outer ring faults with the 2 and 3 severity levels. But later on, we would like to test it on the entire set of the labels and on all the different fault types. So if we compare the performance and average it over all the directions and all the transfer directions, so the baseline now results in 83%. And if we apply the proposed fault signature gun, it results in 96% performance, accuracy performance on average over all the different directions. And here we could not apply the unilateral alignment, because this is really in both directions. We also wanted to see a bit how do the signals that we generate actually look like. Because if you look into generated images, you see immediately how good their performance, the generation performance is, but particularly for generating physics-based signals or engineered signals, it is more important to keep them interpretable. So what you see here is on the one hand the target data set. So this is what we actually are interested in. So this is the green signal. Then you see the real source. So this is the orange one here. And this is really averaged with the distribution, what you see here as the shadow, here the average signal of all the signals in the data set for one fold type and one severity. And the synthetic is the blue one. So it seems to follow actually quite nicely the generated signal. What we also did is we took the difference between the generated and the real one, and the real and the source signal. So the red curve is the difference between the generated and the target signal, and the purple one is between the target and the source signal. So what you see is that the source is not really representing the signal that well. The generated seems to have generated it rather well, except this first part where apparently it's not following it that closely. And this is potentially where we could additionally apply domain adaptation approaches on top to try to align it between the synthetic and the real data. So what we saw so far was that on the one hand, we could transfer the operating conditions and the fold patterns between different units or between different operating conditions. And this is really how we could unlock the knowledge from the fleet. Because this is where we're not just relying on one unit, but where we're really able to transfer the experience between the different units in the fleet. And we can really start monitoring the systems from the very beginning. So we just need to collect a part of the healthy data. And this is when we can start transferring it between the different units. So this was the first part of my talk. And as promised, I also wanted to discuss with you a bit how we are addressing it in a bit different way. And this is where we are combining the physics-based and the deep learning models. So what we saw so far was that on the one hand, we could detect and diagnose faults, but as presented at the beginning, they're also interested on predicting the evolution of the system condition over time, and particularly predicting on when the end of life will be reached. And this is really the predict part. And for the predict part, we don't just need fold samples, we really need this whole trajectories of time to failure data. And this is where it gets more challenging. And this is also where we often need not just to take data, because typically we don't have sufficient data collected in it, but we will really need to start looking into the physics-based models as well. And particularly the part of prognostics, or the part of predicting their remaining useful life, has been really nearly exclusively reserved for physics-based approaches. And there are different directions that we could go. On the one hand, we can start modeling the degradation mechanisms at different levels, or we can really go do a deep dive into physics of failure models. We could also start modeling at the macro level, where we possibly are able to model the cumulative damage, or try to model the fatigue mechanisms at the macro level. But on the other hand, what we can also do is we can start looking into the performance models, where we are not modeling specifically the faults, but where the impact of the faults is modeled on their measured signals. This is really rather at the macro level, and this is has been the focus of the research that I will present to you now. And there have been really many different ways on combining physics-based and data-driven approaches. This has been one of the hype directions recently. And there's really many different combinations between the two. So we can have very little data, but we may have a lot of physics. But on the other hand, we may have a lot of data, and we may not know anything about the underlying mechanisms, and we can have anything in between. And this is why there have been also very different ways on how we can combine them. So we can have some surrogate models, we can apply transfer learning, we can learn discrepancy terms, we can try to model the parts that are not modeled by our first principle models. And one of the most popular approaches has been the physics-informed neural network that has quite a lot of researchers have adopted and followed. So one of the directions that we have been taking has been different to physics-informed neural networks potentially. So what the approach actually implies is that on top of just measuring their data, so these are our scenario descriptors, and this is our measured signal. We also have a performance model. It's just a performance model. And we can calibrate it with our measured data. And once we have this calibration, and once we start calibrating or adapting and updating the model with each of the new inputs, we actually have not just access to the measured parameters and now estimated parameters from the system model, but what we also have access to are the virtual sensors that are not captured by the real process, but we also have access to these calibration parameters that are actually capturing the impact of the degradation on the system performance. And this is what has been used to compensate this degradation in the system model. So what we're actually doing is we are expanding the input space by these physics-based models, by the performance models. So we're not just taking the measured parameters, but also the additional inputs that are only coming from the system model. We applied it on a case study for remaining useful life prediction of a fleet of turbofan engines. And what we're really interested now here in, so when is their end of life? So what is the remaining useful life from the point of time when we are now? And if you follow the health index, what you see is dependent on how their units are operated, but also what the underlying fault type is. Really, the end of life varies actually quite significantly. So that's the underlying framework. We have now 3 parts: so the process parameter measurements, the virtual sensors, and the calibration parameters. And this would be just the purely data-driven part, and this is the part that is coming from the performance model. We feed it then into a neural network, and then we predict the remaining useful life. So we applied it to a fleet of turbofan engines where we collaborated with NASA. We used their simulation model to generate those trajectories and the data. We were using real flight conditions as the flight conditions for the simulated data. It's quite a large data set. For this specific case study, we only used 9 turbofan engines, 6 were used for training and 3 of them for testing. That's just some samples of one flight cycle. We have 2 different fault types that were considered. And as mentioned, we had 6 engines for training and 3 for testing. And this is when we stacked all the flight cycles on each other until the end of flight. So this is just to show how different flight classes actually impacting the different parameters that are captured. So the units 2 to 20, these are our training units, and units 11, 14, and 15 we use for testing. And in fact, unit 14 was flown in different flight categories. So this was rather flown for short flights. Unit 15 was flown for rather mid-distance flights, and all the other units are rather long-distance flights. And I wanted to see how we are able to overcome these differences in the flight conditions and actually in the domain. So this was the framework that I presented to you. We have the real process, we have the system model, we calibrate the system model. Once we calibrate it, we feed in the calibration parameters, the virtual sensors, and the estimated system parameters, and then we predict the remaining useful life. We compared the purely data-driven approaches and the hybrid approaches, and we also applied different neural networks for it. So this is just a feed-forward neural network. So we just take all the inputs at one point, time step, and then predict the remaining useful life. So what you see is that the hybrid approach performs already much better. We also applied convolutional neural networks to it. So on the one hand, we have an improvement in the data-driven part here from the feed-forward to the convolutional neural network, but we also have quite a significant improvement now here for the hybrid part. We also quantified the results. We have quite an improvement between the data-driven and the hybrid part. So we use the RMSE for performance evaluation and the so-called scoring function that actually penalizes the cases where the algorithm predicts longer remaining useful life than the actual one, because this is kind of the critical part, and the under predictions are penalized less. We also applied LSTM to it. Again, the performance between the data-driven and the hybrid is quite significant. The CNN performed actually the best. So we also wanted to see what is actually their when can the user start trusting the algorithm, because this is where, for example, the error bound of 5 cycles is not left anymore. So at what point in time do we reach such a prediction accuracy that it does not leave the error cycle, the error bound of 5 cycles anymore? And what we see is that we can improve the prediction horizon when we are really sure when the end of life would be by more than 100%, and for some units it was even by 200%. What we also wanted to see is what happens if we reduce the training data size. So we had 6 units at the beginning, so this is just what you saw before, the same results. But now we train it on a smaller data set, so we just take 3 units and test it again on the same. What we see is that for the data-driven part, we have a performance drop. For the hybrid part, for the hybrid algorithm, we have about the same performance, or depending on which performance metric we use, it's plus or minus 2%. And it's a reduction of the training data size by 50%, and the performance level is actually maintained. So what we're able to achieve with this hybrid approach is really, on the one hand, a better performance. We can reduce the training data size. We can generalize better. But we also can interpret the results in a better way, since we're providing more information to the decision makers. I actually wanted to share with you some 2 additional approaches that we are working on in terms of the hybrid algorithm. But I think we don't have time for that anymore. If we don't have questions, we can come back.
Yeah, 20 minutes left.
Oh, okay. So then I will present shortly to you the 2 other approaches that we have been working on, and that go a bit in a similar direction, but really take a different take on how we can combine data-driven and physics-based algorithms. So one of the directions that some of the research groups have been pursuing is to first generate data from the first principle models, use this simulated data and to pre-train the model. So obviously we will have some parts that may not cover everything that we're interested in, and depending on how good the first principle models are, this depends also or determines the performance of this pre-trained model. But what we can do afterwards is, if we have access to a small part of the real data, we can then use it to fine-tune our model and then apply it to real data afterwards. So that's a bit the basic idea, and where we tried it on is on predicting the discharge cycle of lithium-ion batteries. And the lithium-ion batteries have been applied on quite a broad range of applications. And one of the challenges there is to really be able to precisely predict when the end of charge will be achieved, so that we are really able to use it until the end of charge is reached. But one of the challenges that we are facing there is that depending on the degradation level of the battery, then the prediction accuracy drops or changes quite significantly, with influence by the current degradation state. So if we just look here into the different degradation states, and this is just a constant current that is applied here, so it varies quite significantly depending on how degraded the battery actually is. And it's quite difficult to infer what the degradation state is and to determine it. So particularly for very or for expensive applications, it can be inferred, but this is not what we're really targeting. What we would be like to be able to do is to use a small portion of the data in order to be able to infer the degradation state precisely. And this is the architecture that we propose. So what we're using is the first part of the context from the voltage and from the current measurements. And from this, we concatenate our context representation. We then encode it into our encoder that infers for us implicitly the aging state or the degradation state of the battery. What we then do is we use the predicted or the planned current profile. So this is how we are planning to use the battery. And then we are feeding it into the decoder together with the inferred aging state, and then condition it on it and predict the discharge cycle of the battery. So what it really enables us to do is, on the one hand, to handle quite long time series, to infer implicitly the aging parameters, and then to predict the discharge cycle precisely. And we evaluated it on many different conditions, on many different load profiles with different complexity levels, and with different length, with different duration, and it really performed rather quite well. Well, what we also discovered was it's probably not so well seen, but there is still a gap between the real data and the simulated data, particularly at the end of discharge. So while the model that we use, where again we partnered with NASA on it and use actually their models for it, the models are already quite good and they're predicting the discharge quite well, but particularly the last part was not modeled that well by this particular model that we use. So now when we apply just a couple of real discharge trajectory from real data, we are then able to close this simulation to real gap and really start following the real discharge trajectory. So this is just for one discharge cycle, But if we combine all of them, and this is demonstrating that particularly at the end, there was quite a large gap between the real data and the simulated data. And now when we apply this fine tuning on top, it really closes the domain gap and it enables us to predict quite precisely. The second one that I wanted to mention is really just a flashlight on it. It's the direction where we actually are using for predicting precisely the particle interaction, really at particle level. And we actually combine two parts of prior information there. On the one hand, we use the inductive bias, so the structural information of the particles, and on the other hand, we impose the underlying basic physical laws during our training, and this is how we obtain the final model here. So this is the architecture that we were using. So on the one hand, we are applying graph neural networks to it, so we're using the structural information from the particles. And on the other hand, so the second part that we are using, that we are imposing the Newton's laws on it in order really to predict the acceleration quite precisely. So our goal is by predicting how the particles move, inferring the forces and the potential energy from the particles. And it's really just a flashlight that there is really different ways on how we can combine or how can we bring in the physics-based information into the learning. And this is what I started with. These are the challenges that we aim to address. So we need to overcome the challenge of missing labels. We also need to have discharge trajectories, degradation trajectories that we need to use for training. We are facing the challenge of the very diverse operating and system conditions, and we need to make our models better interpretable for the decision makers and really to make it as generalizable as possible. So what I presented to you is particularly in the core of our research. These are the first two layers that I presented to you. We have a bit other directions on top as well. So what remains for me to do is to thank particularly to my team, since I'm the one who is presenting and all the work has been done by my team, and to our past or current industrial project partners, and to the funding agents. And I'm happy to take any questions or discuss any suggestions or comments or ideas. Thank you very much.
Let me say some words of closing for today. Thank you so much, Olga, for your time and your talk. Thanks to you all guys on site and online. This was our first talk after the summer break. So we're looking forward to see you all soon again on 5th of September for the CIS Get to Know You Later talk with Philipp Schwaller. And then I hope you've seen it already. We have the Riken ERP EPFL CIS hybrid workshop coming on 7th and 8th September. All people at EPFL, please sign up because there's going to be coffee at lunch. We have to manage that, and all speakers are going to be there first to take advantage of mingling again with the people on site. And of course, all the partners and colleagues from Riken ARP, they're going to join online. Thank you so much, and I wish you a nice afternoon. See you soon. Bye.